things of what quantum information means in terms of the bit string that classically it is 0 and 1 combinations, a string of zeros and 1. Here there is something more like the vectors, the computational basis vectors 0 and 1. They are required to represent any vectors, quantum state vectors, get psi. And there is an associated probability amplitudes alpha and beta, which carries the uncertainty of the basis states 0 and 1, not just the 0 and 1, but the uncertainty of the 0 and 1, right? Of the state to be in 0 and 1, right? So certain things just we have seen. Now slowly let us start. The quantum information we will just start now. Sorry. Okay, I'll be back with the measurements, various measurement scheme, orthonormal basis, these things again, no worry. But as we are starting, let us define more about the quantum informations, right? So even just what we have learned, even without noise, because in the first step we have considered noiseless case, right? Noiseless case. Even in the noiseless case, we have uncertainty in the quantum state with the probability amplitudes alpha beta to be in the state ket 0 or ket 1. There is an associated probability alpha square beta square, and the state is represented as ket psi equals to alpha ket 0 plus beta ket 1. And these alpha and beta are the uncertain quantities, amplitudes, right? The complex coefficients with the additional constant that alpha square and beta square equals to 1. Because the total probability of the state to be either in the state 0 or in the state 1, but the entire probability is equals to 1, right? And in the continuous wave function definition, basically, if this is your initial state x1 and this is your x2 and this is the wave functions representation psi of x, then integration of psi square x dx from the point x1 to x2 equals to 1. That is, we have seen from the probability postulate or the quantum postulates for the wave functions, right? Equivalent in the quantum physics or in the quantum computing part. They are same. Now, till that point, there is no additional uncertainty, but information in the quantum system that is basically described in the Hilbert spaces, that means the vector space where these quantum states are basically belongs. That means earlier any ordinary u and v, we are saying this belongs to the vector space V. Similarly, the quantum state psi, it has some additional property. So that property basically it belongs to another vector space, which we will call a Hilbert space H, which is just like any other vector space, just a vector space itself with an additional constant that it has an inner product. Okay, so I shared certain notes that all the details of Hilbert space and their properties are discussed. Now, where this psi is generated, like in somewhere in some hardware it is generated, right? Even like I have to create this information on some physical device, right? Physical device. And this physical device, when I try to generate this psi every time, so there might be even if I try with a very certain alpha and beta, still there might be certain uncertainty due to the device error or the controlling device error, right? Or the various atomic behavior like Brownian motions, other things, the heat, thermal effect, and many other things, right? So psi may have like the psi I try to generate that may be noisy because of either its generation or the processing of psi from even it I say it is passing through some certain evolution with identity. That means it does nothing to psi, but still if it is a physical device, so there will be an interaction with the environment, right? Somehow, and there will be loss of quantum information, or there is a interference of the quantum information with the environment and all. So we'll look those things in the open quantum system later. But for now, suppose this ket psi is not a pure description of the quantum state. Hence, basically, we have a ket psi, right? and this ket psi will have many representations, say ket psi 1, ket psi 2, and ket psi n, many such n number of realization it can have, and then all this. So that means this alpha 1, alpha beta, say for example alpha 1 beta 1, alpha 2 beta 2, alpha 3 beta 3, and alpha n beta n. For each such representation, the values can be changed, right? There can be because of the noise, they can be actually different in each representation. So this is called the ensemble representation or ensembles of quantum states, right? So once I see that there is an ensemble of quantum states, right? So immediately I can assign probability because there is uncertainty. They are random variables. These all these vectors, quantum states are random variable now, and each random variable might have an associated probability. For example, this quantum state appears for certain number of times, right? So hence it has a probability, say P1, it has a probability P2, it has a probability Pn. So each such noisy state may have a probability how many times those states repeated, etc. Right? So then I can define in a way that why just the ensembles of state, but I can have a probabilistic description that there is a probability associated for the state representation ket psi I. Okay. Right. So this is a better ensemble representation of a quantum state where there is a quantum particular quantum realization ket psi I, ith realization with an associated probability pi. Ensembles with an associated probability, right? So additional term is coming because the system might be, or the generation of the quantum state might be noisy. There might be more number of realization, and each such realization has an associated probability, right? So I can represent a general representation that any state representation ket psi I has an associated probability p, right? Now, if you have, say, for example, 5 state and 5 probabilities of those states, so that particular time it will become the PMF all many state, right? Probability mass function of states, state vectors, right? Of states. So if I take for some I equals to say 1 to certain number of n number of representation of the states with the associated probability, then I'll get a probability mass function. Say this is for the first state, the probability this much, second state, the probability is this much, third state, the probability this much, fourth is this one, and so on. So I'll get a probability mass function of the states versus the probability, right? So probability mass functions, a representation of the states. Because in the information theory part, we are taking the discretized version. That means discrete random variable. So if it is a discrete random variable, then there is an associated probability mass function which measures or which help us to tell us or to help us that what is the on an average information out of these things. So we'll define entropy and certain other things with this associated probability mass functions pi. Okay, later. But now it is difficult, in fact, to represent information in this ensemble way. What is the better way? So people have come up with something called a density matrix, and the definition of density matrix is given by. So this will just help us to represent our quantum information for the noisy systems. They can be equally represent our noiseless case as well, but they help us a lot for the noisy quantum systems. So the definition is, so suppose a statistical ensembles of pure states. Now there is something called pure state, mixed state. I'll come. Okay, no worry. So okay, let me first define with respect to the pure state. Then I'll come to the noisy state. That will be, I think, better, easy for us to understand. Okay, so a density matrix is basically represented by rho, and from linear algebra, by its property, it is a positive semi-definite matrix. Positive semi-definite matrix. And those who have attended my linear algebra classes, you have seen a very good decomposition techniques for PSD matrices, because for any unit vector xp x greater equals to 0, so a good decomposition exists called the Cholesky decomposition, LL transpose part, to decompose PSD matrix into lower triangular matrix. That's a different thing. But for now, and also it has another beautiful property that all the eigenvalues are non-negative, basically positive in this particular case, right? So positive semi-definite, right? Semi-definite, for the semi part, I have put the 0 and the greater equals to. If it is positive definite, this equals to part will be removed, strictly positive, right? So density matrix rho is basically a PSD matrix or the PSD operator with trace equals to 1. Okay. So trace of the rho equals to 1 and rho is greater than equals to 0. That means a better way I can write as x is some vector, unit vector, x rho x greater equals to 0. Okay. So it represents a quantum state. Now we'll represent a quantum state using a positive semi-definite matrix, PSD matrix rho, right? Because the trace equals to 1 and it is strictly greater equals to 0. So we can represent a quantum state as rho equals to outer product of the states psi and psi. So earlier we had a quantum state. By state we meant uh, it's a Kate psi. That means a column vector, in fact, right? Column vector which is normalized with complex coefficients, that all its coefficients are belongs to complex. If it is n cross 1, so it is complex n cross 1 coefficient vector, right? C n cross 1 column vector. Now we just redefine the state to a matrix now, from a vector to a matrix. And that matrix is a positive semi-definite matrix, just the outer product with itself, right? So in fact, why it will help us when we'll do the measurement, we'll see like how we represented a measurement basis into 0, 0, 1, 1, and so, right? Similarly, this representation will help us in the POVM and other measurement cases as well. So for now, just extending the definition from a vector to a matrix with some additional property that trace equals to 1, and it's a positive semi-definite matrix that x rho x greater equals to 0, right? And this particular definition is called density matrix definition, or the density matrix representation of state. Representation of quantum state. So for now, we'll simply call a quantum state is rho. Okay. And when we'll do quantum computing, we'll say it's a psi. When noisy quantum computing, we'll say again rho. Okay. So it's basically whether it's a Kate psi or rho, it's a fine, no issue, right? They are equivalent. These two things are equivalent. Okay. Now, if it is a definite pure state, right? It's a pure state. We'll say for a pure state that there is no uncertainty in the generation of the state psi, pure state Kate psi. The density matrix will be simply the outer product of psi, and there is no associated uncertainty in the generation of psi for the pure state. But in case it is a mixed state or impure state, so how many such states are there? Because their ensemble representation is an associated probability and a quantum state psi, right? Any quantum state, a set of quantum realizations get psi I with the associated probability pi, right? So this probability is not alpha beta. Okay, this is not alpha beta. Do not confuse these things. This is coming from the generation or the uncertainty in the state psi. But of course, this pi has something to do with alpha I and beta I. Okay, there is some relation, but they are not equal. Now the density matrix will be defined as summation of Pi outer product, the same outer product psi and psi. This times it is psi I and psi I, okay, and Pi. This is the probability associated. So let me make the eraser. Pi outer product of psi I and psi I. That means what? So every time I have one realization, say if the first realization is psi 0 and psi 0, this is the pure state your quantum state rho 0, right? Again, say psi 1 times psi 1 outer product, it will be rho 1. So I take a combination. The first state of pure density matrix rho 0 has the probability P0 times rho 0, say, and the second state P1 has the probability P1 rho 1, P2 rho 2, so on, Pn rho n, and I will have the entire state rho, and I will call that rho as a mixed state. Only it has to follow, it should be a positive definite matrix, and the trace equals to 1. And you can easily see because it's a sum of probabilities, and we all know that the sum of probabilities equals to 1. Hence, any mixed state has also the trace preserving property, right? So density matrix provide a comprehensive way to describe quantum states, especially when dealing with uncertainty or incomplete knowledge of the system. So it will help us to describe quantum system with incomplete knowledge. Incomplete knowledge about the system. What is the good part? Good part is that now your input is earlier your input was a quantum state. It was passing through a unitary evolution by Schrodinger equation U, and then you are getting some another quantum state phi. Now your input is itself a matrix, positive semi-definite matrix rho. It will pass through some evolution psi, and it will be another something say sigma is your next state. All three are matrices now, right? And immediately you can basically so the two equivalent equations. So here the equation was your equation was psi t evolved state equals to e to the power minus iht psi 0. This was your Schrodinger equation, right? Psi 0 at t equals to 0. And immediately from this, we can say evolution of a quantum state in the density matrix rho hat equals to minus I by h bar. Okay, just I removed all these IH things from here. You can put it like del t and those things. So after the derivation, you will be getting the solutions, right? So this is equivalent to your I del t psi t equals to h of psi t, right? This is the Schrodinger equation and this is the solution, right? After the time evolution solution. So similarly, evolution of a quantum density matrix equals to I h bar commutation of h t comma rho t, if rho t is the initial states, right? So this particular equation, so I'm not going detail of this. It has nothing to do in the information part. So this is called Liouville von so same thing but differently. Let me put this part again a little bit bigger size so that you can, if you want, you can take a copy note of this. Okay. So now we know how to represent a noisy quantum state, right? Earlier we learned how to represent a quantum state in the basis 0 and 1 because it has a probability alpha and beta. So simply you can write it as a column vector alpha and beta. Now you know if there is uncertainty or incomplete knowledge of the system, I have a better representation by rho. and I can assign a probability that there is a probability pi associated for a particular realization psi I, and I can in fact define that rho equals to pi outer product of psi I, which is a probably basically outer product of the states, which is a matrix, and that matrix is basically a random matrix. It's a random matrix, right? So, and basically by property, it's a positive semi-definite PSD matrix with a trace equals to 1, as well as x rho x equals to greater equals to 0. That means it has all the non-negative eigenvalues. Eigenvalues are also greater equals to 0, right? Any doubt with this? I'll pause for 1 minute, say, and then slowly. Now everything is just by definition. This is the fundamental concept of quantum information, as I know, because I mean it has a lot of other things I don't know, but at least the basics is this one. On top of it, we'll go slowly. What is like entropy, other quantities, various matrices, and other things we'll slowly cover, right? So if you have any question, please feel free to put it here. Now we'll define various metrics. So I'm waiting still for any query or anything, maybe a couple of seconds, few seconds. Well, so as there is no question as such, so now how we can measure the similarity or the uh, or the or the distance between two quantum informations, right? So there are certain metrics like static and dynamic metrics. So let us pick some of them. One is called the fidelity. So fidelity quantifies the similarity of two quantum state, uh, this rho and sigma. So we'll measure the similarity. Similarity. So what do I mean by this rho and sigma? Is that suppose okay, even before definition, let us uh, try to visualize this thing. Suppose you are sending a quantum information Kate psi to your friend sitting from Delhi to Bangalore, say Kate psi, and your friend receives Kate phi, right? And there may be uncertainty in both the places, in many places, right? So here there may be a lot of noises in the transmitter itself, and you have a density matrix representation rho, and whatever your friend receives, so they have a matrix representation or the density matrix representation at sigma. Now we have to measure how much these informations are similar to each other, right? Ideally, this sigma should be equals to rho. That means whatever is transmitted and that is received. But we need to calculate the like closeness, right? Or the similarity, that is called the fidelity. And it is defined as, okay, there is a question. Can you elaborate on the evolution of density matrix? Okay, just okay. So I shouldn't cover these things. This is the commutation relations coming from the Liouville von Neumann equation. So we have both the representations, right? So one is with respect to the Schrodinger equations, right? Like the state is the evolution of a state, right? Evolution of a state, time evolution of a state is related with its Hamiltonian, right? Which so I del t psi t equals to there is a h bar part also. I h bar del t psi t equals to h of psi t, right? And here the time evolution is represented in terms of the quantum state psi, right? Similarly, the density matrix del t of rho t is related with its Hamiltonian as a commutation of HT and rho t, right? I'm not giving the details because this is out of scope of quantum communication. So maybe sometimes later we can discuss this in some other portions. But yeah, so these are two equations for the state and the density matrix cases. So there are many in between steps like the Schrodinger picture, Heisenberg picture, the Von. So there are lots of things. So I'm skipping those parts here. But at least if the density matrix evolve over time, what will be the equation? I'll come. So suppose we have transmitted kit psi. In the transmitter, say it is Delhi, and in Bangalore or in Kanyakumarika. So there we receive the state phi, kit psi and kit phi. But the density matrix, that means there is uncertainty both in psi and in phi. So we better represent them by the density matrix rho and sigma, right? And then what is the similarity between these two informations, right? So here we'll define a metric f of rho and sigma, right? That is equals to trace of square root rho sigma square root rho. Okay, this is just the definition, right? So this is the definition of fidelity with the density matrix. Now there is also, instead of if you say, okay, I have no uncertainty in ket psi, right? And I receive only ket, say ket phi. Okay, so this is what I transmitted and this is what I receive, right? So what is the fidelity? For that particular case, the fidelity definition is the square of phi inner product of phi and psi. This one. This is called the fidelity. And there is a quantum circuit to calculate the fidelity called the swap test circuit. Swap test quantum circuit. So in fact, I can give a drawing. I'll not explain. This looks like this. We apply Hadamard here. So there is a detailed calculation. I'm just avoiding it. So if you just measure it here, the probability of 0 and 1, specifically if you measure the probability of this ancilla qubit, you can calculate the probability of the inner product of these two state phi and psi, right? So this is called the swap test circuit, where if you assume that there is no ensembles of psi, I am very much perfect in my quantum hardware, you can calculate this. But from the information theoretic view, of course, there might be some uncertainty in phi and psi. Then this is the fidelity definition, right, with the density matrix. So two definition. This is one with the uncertainty in phi and psi, and this is with certainty or noiseless case, right? These things. How can we eliminate the noise in quantum channel? Is there any specific algorithm? Every company is trying. Okay, every company, every organization is trying to mitigate noise. So there are special techniques, noise mitigations and noise suppressions. And people are also trying towards the fault tolerant quantum computer, where they are trying to basically so it's not possible to remove the noise, but it is the way intelligently how you can mitigate the noise, means how you can maximally retrieve your information out of it. So suppose there is a source of I mean, so error corrections will give us the better answer basically. So I'm not covering what is error correction, but the basic notion, if it is a repetition code. So um, suppose I should receive, this is my suppose a particular spin, right? So now after measurement, I can get this particular spin or I can get this particular spin, right? And because of noise, this particular spin can become this one, right? Or because of noise, this particular spin can become this one, right? Or the ket 0 or ket 1 if you define. Suppose this is your ket 1, it may become ket 0 or ket 0 may become ket 1, for example. But instead of a single particular quantum system or a quantum circuit, if you have a multiple such representation, right? And you see on an average, in the measurement case, you get say out of 10 repetition code, if you see that most of the codes are giving you 0 and only 1 or 2 are giving 1. So by majority, you can say, okay, it is maximally Kate particular Kate 0. So my information is Kate 0. So this is a part of quantum error correcting code, right? Repetition code. So there are certain error correcting codes. So maybe other experts will take some sessions on that. I'm not covering these things. But yeah, so those are some techniques related to that. Yeah. So now let's define another metric that is called the trace distance. So we have some another 15-20 minutes. Let's use that time. Our state is at micro level and your pointer is macro, noise will be there. I did not understand the question. Okay, fine. So I'm using a digital board and it is sometimes it creates a lot of issues, multiple because of changing multiple devices. Okay, so the earlier was one to calculate the similarity of two informations. Now the distinguishability of two quantum states. We can calculate the distinguishability of two quantum states given by d rho comma sigma. Okay, this gives a distinguishability measure. How far is a quantum state from another state, right? So this is equals to half of trace and the difference between these two metrics. Very simple one. Trace. So difference between these two matrices, so rho minus sigma, you take the mod. So it doesn't matter. You take sigma minus rho or rho minus sigma and trace of that particular thing and half of that. This gives us the trace distance between two metrics and it gives us a measure that how much a quantum state is deviated from other state, right? So you can immediately ask me, I can simply minus these two states, right? But you mean whether quantum postulate will basically validate or not. So that's why these normalization factors and all are coming, right? Because the probability sum in that particular state also should be equals to 1 and so this is a of course it's a distance measure, so there is nothing to hold the probability law, but it's a easy way to measure the informations in the normalized form, right? So these metrics are fundamental in evaluating performance of various quantum protocols, quantum error correcting codes, and the reliability of quantum operations. Now, as we have learned the entropy, right? So entropy is basically measure of your uncertainty. Like in simple definition of entropy is the expectation of the probability, right? So probability mass functions that represent your classical information. Similarly, there is some term called the quantum entropy that will measure the uncertainty, resolution of uncertainty in quantum, what we call quantum Shannon entropy. So what's the definition? In quantum information theory, entropy generalizes to account for unique features. I'm writing in a very vague sentence so that easy to understand form of. So entropy generalizes to account for unique features of quantum systems. The von Neumann entropy or the Shannon quantum entropy sometimes. So the better term is called the von Neumann entropy, more specifically because the entire chapter is Shannon information. So within that, this particular definition is called the von Neumann entropy, is a direct analog of Shannon entropy. Shannon entropy more term is called in the classical context. That's why I put the Shannon quantum entropy or the von Neumann entropy. So it's defined for a quantum state by a density matrix rho as S of rho, which is basically von Neumann entropy equals to minus of trace rho log 2 base rho. So earlier in the classical entropy definition, it was P log P, right? Minus P log P. Here it is minus trace of rho log 2 base rho, right? So now I'll give 1 2 questions. So of course, in the density matrix definitions, we have certain things. Rho equals to positive semi-definite. That means rho equals to rho dagger. It's a Hermitian matrix. It's a positive semi-definite. Means rho x greater equals to 0 and trace of rho equals to 1. These are certain properties of the pure and impure, pure and mixed states. I mean represented in the density matrix form. But let us do some example. Okay. Example 1. Suppose consider a qubit is in the state ket 0 with probability equals to half, and in the probability in the ket state 1, right, with probability equals to half. So half of probability, that means you applied the Hadamard gate in front of the 0th qubit, suppose, and you do the measurement and you get the half of probability, right? So means you start with the ket 0, you apply a Hadamard gate, and whatever state plus state you do, you do repeated measurements, say 100 times, and you get 50 times ket 1 and you get 50 times ket 0 theoretically. So you get a probability like probability of half and half for both the case 0 and 1, right? This is the scenario. Now just calculate what is rho. What is rho? Can someone quickly try this one? And there is something called a purity, a definition, purity of a quantum state. That means how much uncertain a quantum state itself is called the purity. And the definition of purity is trace of rho square. Okay. So for this problem, calculate what is rho and calculate what is trace of rho square. Okay. So we just calculate it, and then because rho is another part, because rho is a PSD matrix, so it can have a spectral decompositions, and we can write the eigenvalue decomposition or spectral decompositions of rho matrix as sum over I lambda I, the ket I ra I, that's the outer product of the IZ vectors, lambda I, ket I. These are basically spectral decompositions of the matrix rho, right? So so we can write it as, we can write the A sub rho entropy formula as also sum of I lambda I log 2 base lambda I, right? You can check the proof from like as a homework. So immediately this formula that was earlier, this one, this is also equals to minus of trace of sum over lambda I log 2 base lambda I. Lambda is the eigenvalue of rho, as simple as it is. So immediately it becomes a simple formula of eigenvalue equations. So somebody is answering answer equals to 1. See, I asked the first one. Okay, trace of the second answer. The purity is equals to half. This is correct. And the first answer will be identity by 2. Okay, identity matrix by 2. So tomorrow we'll start Krauss operator, various quantum channels, and today also let me give one or two more examples maybe for simplicity. And tomorrow maybe we can touch little bit of Markov process, quantum Markov process. And okay, let me give one bound today because it will, we have some time. So maybe there is one bound called the Olivo bound of quantum information. So if we have learned channel capacity, right? How much information can be transmitted over a classical channel, right? Now you can see quantum system itself is so uncertain, and I can always create like arbitrary amount of, I can always, because the quantum system is highly uncertain, I can do a lot of superpositions, right? So what do I mean is that if I have two quantum information, say K0 and K0, I apply a Hadamard here, I apply Hadamard here. So I have a plus, I have a combined state. So combined state with what are the possibilities? 0, 1, 1, 0, 0, 0, 1, 1, 0, and 1, 1. These are the possibilities, right? Basis states now. From 0, 0 to these are all four possibilities. And basically, if I can create equal superpositions, all have the 1/4 probability, right? So that means if it is a plus state, it's highly, highly uncertain, right, of a particular basis, right? So because all are equally possible, so I can create many such, with many such qubits, I can create lots of quantum informations, right? But can I, because my information that I want to see, I have to do quantum measurement, and if I do quantum measurement, I'll get back the classical information back, right? So how much classical information I can get out of a quantum system, quantum informations, right? And that particular case is given by Oliver bound. We will not derive this bound, so you can consult with any standard textbook. But what is the theorem? For an ensemble, for an ensemble of states, for an ensemble of states, and by ensembles I have to give a probability concept and a row concept. Okay. Okay. Let me define one more term. So, uh, I may have uncertainty in psi. I may have an associated probability pi, and that's why I have defined something called the density matrix, right? And that is, which is basically sum of pi, outer product of this and this, right? But it may be the case, even if you have created density matrix rho, but the density matrix itself can have uncertainty, right? And that is called the ensemble of ensembles. Ensemble of ensembles. That means even after creating a density matrix rho, if I have even uncertainty of the density state rho, then I can have an associated probability, say instead of pi, let me write qi. Let me write qi with the density matrix rho I. So this is another set of ensemble representation called the ensemble of ensembles, okay, or the ensemble of states now. And this is basically another level of uncertainty coming in the density matrix, right? So for an ensemble of state, that is pi rho I, not ket psi I, rho I, the accessible information which which is the maximum classical information that can be extracted from the quantum system, can be extracted from the ensembles or the ensemble states is bounded by this theorem, Olivo bound theorem. And because I said it's the maximum classical information, hence it's an upper bound, right? Upper bound of classical information. And that is I accessible is always less than equals to ensemble pi rho I. So this particular quantity, that is the information representation of this uncertain ensemble, right? So it equals to S of summation pi rho I for I minus summation pi S of entropy of rho I. So this is a bound, how much maximum classical information I can extract from a uncertain quantum system is given by the Hollywood bound. And this bound implies that while qubits can hold immense amount of classical information, that means whether this alpha Ket0 and beta Ket1, I can have huge possibilities of alpha and beta quantum mechanically, right? But the amount of classical information that I can retrieve, I can access, right? It has a limit, it has a bound, right? Classical information we can reliably extract from the ensemble is strictly limited, and that limit is given by this particular bound. So with this, I conclude for today's session, and please feel free to put your questions, and I'll be happy to take the questions for today or tomorrow. And thank you for giving time.
Thank you, sir. Thank you very much. And it was very nice to listen you.
Thanks a lot.
You started with the very basics, right?
Yeah, I started with very basics, and initially I confused as sir, yeah, just the organizer before you told that all the basics are covered. So I was a bit fast. Then some of the participants told, no, this part is totally new. Then again, I started very slow so that people can get it. And I shared the important resources, like those who are really interested in quantum information, they can go in depth. Usually these topics are a bit complicated and difficult, and I'm
Yes.
trying to make it as simple as possible because of the diversity. Like many people are coming from various backgrounds, like biotechnology, other various departments, so they do not feel awkward or something like that. Yeah.
Yes. No, this very wonderful section. So thank you very much. Thank you all for your kind patience. And I think you have already given the answer to all the questions, right?
Yeah.
Yes. Thank you so much. We are closing this session. Bye bye.
Bye.